I want to move on to our last speaker for the session. We're running behind here. Okay. So our last speaker, Alex Gorodetsky from the University of Michigan. He's in the aerospace engineering department there, and he's going to be talking about scalable learning of dynamical systems. And take away, got everything set up?
Yeah.
Okay.
Can you hear me in the back? Okay. So today I'll be talking about scalable learning of dynamical systems, which could mean anything. So I put a little bit more of a direct title, which is low-rank approaches for increasing computational efficiency. So before I start, I was just wondering how many of you have, for instance, used tensor decomposition approaches in any of your work? Okay, so probably no. So this work will be focusing on these types of oriented approaches for improving computational efficiency. So I come from a little bit of a different motivation than maybe the previous speakers before. So I'm interested in learning in the context of decision making, and specifically if we have, for instance, robots or small autonomous systems that we want to send out to operate autonomously. So for instance, swim in the ocean or fly in the air through wind or dynamic soar. And the idea is that all of these robots may be governed by, let's say, 20 degrees of freedom, but they may be operating in very complex environments that, for instance, are like fluid dynamics environments they have to model. So the idea is how do we learn enough so that we can make decisions and in an optimal way and in a way that is suitable for general design, control, and optimization. And when I talk about scalability, I'm really looking for these three types of characteristics. One is I want to minimize the number of data I need in order to learn something that's sufficient for my purposes. I want to reduce dimensionality in an aid to kind of reduce the data requirements, and in an aid to increase the speed of computation. So this is what I mean here is that typically you've seen your neural networks or different general machine learning models are built because you want to evaluate them quickly in order to query. But here, maybe these things need, these autonomous systems need to make more complicated decisions that just query doesn't make sense. So maybe they need to, for instance, build complex algorithms with their machine learning models. So for instance, if you want to add two learned models together or multiply them together to build a calculus of operations, you have to build your models in a way that's amenable for this. And in particular, the goal is, and this is a bit aspirational, not directly targeted, but kind of work towards, is that we want to be able to do as much computing as possible on board and in real time. So in an idealized learning setup, the way kind of I'm going to view the world is that we have this set of models, that we have an evolution of a state. The state is never observed. It's denoting really the physical representation of our system, and the state it typically evolves in continuous time, and we only observe the state through these measurements. And we can often impact the world through controls, which here are monoparameters, but just you can think of it as monoparameters or controls as well. Now the state, this evolution is often unknown or partially known. This measurement model is often known, sometimes it's unknown as well. And so this is kind of a broad viewpoint of the setting in which we're considering learning. And so in this talk, I'll just focus on two aspects. One is how do we learn quickly if we have lots of good input-output data, and this can be in the context of linear systems. And second is how do we learn quickly if F is nonlinear with no stochasticity. And the main class of tools, and I say class of tools because it's not one tool, there's a large amount of structured methods fall in this class, are low-rank tensor decomposition methods. So low-rank tensor decomposition methods, and here when I mean tensor, I mean multi-dimensional array, although more generally it means multilinear function, which I'll get to as well. They've already been used quite a bit to accelerate a wide variety of tasks in machine learning and applied in science and engineering more generally. As an example, just to show you where they can be applied, is there's now been several recent works and more coming out where you try and reduce the number of parameters in neural networks, which could have hundreds of millions, for example, in the state-of-the-art models. And these can be done by, for instance, assuming or embedding low-rank tensor structure, but not in the terms of matrices, but in the terms of tensors in these types of layers. There's also been nice work showing that large-scale scientific data, for instance, generated through very high-fidelity DNS simulation, actually has a lot of structured information that can be exploited and compressed in order to aid visualization, analysis, and these types of things. And then, as I said, you can use structured learning, structured representation formats to actually create new algorithms. So here, I have this recent work where you can actually solve large-scale dynamic programming problems where you solve by assuming the solution is low rank, and you kind of build an intrusive solver exploiting this representation. So I'll present these ideas in the kind of context of two case studies. One is through linear reduced order model, where the scalability issues arise from large numbers of outputs, inputs, and long observation times. And the key idea there to keep in mind is that we're going to replace the SVD, which is expensive, with another more computationally efficient low-rank representation called the CUR. And the second will be an approximation of nonlinear systems. So scalability issues also arise in this context through the number of parameters describing your parameterization as well. And then as a result, when you use nonlinear parameterizations, because you want to be very expressive in your models, you want them to express a lot of things, the data requirements tend to increase as well. And so the key takeaway is that if you, in all these learning technologies, if you just assume the reduced order structure exists and you can exploit it, then you can dramatically improve scalability. And here what I mean by assume and exploit is I mean that just assume that there's a low rank decomposition and model it as such, rather than discover, which I think of, for instance, a singular value decomposition as discovery because it progressively builds up a higher rank decomposition. Okay, so this is the key point that I'll talk about in the context of these two case studies. So the first study is in terms of reduced order modeling for linear time-invariant systems. So in these systems, we assume we have an underlying system that evolves according to this linear equation. And here we have input systems which we can perturb so that we can perturb the output of the system in order to actually learn how it works. So we want to build a map from the input system U to the output Y. So this map takes the form of it's a linear map, where HI are called Markov parameters. And so these Markov parameters, if you perturb in the right way, this matrix has a nice structure that you can form. I'll show you in a second. And you can also interpret these Markov parameters in terms of the state, in the state matrices of the system. So what we're going to do is we're going to perturb with some sequence of controls, then we're going to sample the outputs yk, and our goal is to reconstruct the system, but more generally reconstruct a reduced order model of the system. And so here I'll show you the Hankel matrix. So this is we've arranged these kind of map, this map that maps from the inputs to the outputs into this Hankel matrix, and you can see that in terms of the system matrices, this representation has the following block matrix structure. So now that you see this block matrix structure, you can factor out the Hankel matrix into observability and controllability components. And here we begin to see that there may be a natural low-rank structure that we can exploit. So the idea is that we want to approximate the Hankel matrix in a low-rank form. And once we do this by computing this theta and this gamma, we can then reconstruct a low-order, reduced-order model of the system by solving a linear least squares problem. Now, in order to reconstruct the system in a way that ensures stability and has some nice analytic properties, we need these matrices to have some sort of properties. In particular, there's this balancing condition, balancing and orthogonality condition, so that you can think of these as kind of rank R reduced order observability and controllability matrices. So the name of the game is that if we have this HR, if we can come up with a theta and a gamma, then we have a low-rank decomposition of the system. So the name of the game is how do we do this very efficiently when H is very, very large. So this algorithm is known as the Eigenvalue realization algorithm. It came out in the 1970s, and it uses the SVD because this is maybe the most natural thing to do. You take HR, you form its singular value decomposition, and then from the singular value decomposition, you can find the theta and the gamma matrices from which you can do whatever you need to do to find the reduced order model. So what we're going to do is something different, and it's to use the CUR decomposition. So the benefits of using it is that it's going to be a much faster algorithm. It won't require all of the data to be loaded into fast memory, so we'll have tremendous speed up, which I'll show an example. And we can prove that under certain conditions, the reduced order models are stable, and we can bound the algorithms, bound the errors. So the COR decomposition has a long history and used in a wide variety of areas. And so you can consult these papers as well. And we'll use a particular flavor of the algorithmic approach in order to kind of meet this requirement so that we don't have to load or go through all of the data. So the COR decomposition has the following philosophy. When you want a low-rank decomposition of a matrix, you essentially want vectors that span its column and its row space. The singular value decomposition finds these vectors so that they satisfy some orthogonality condition. But one thing that you can do is if you take a matrix and you take some linearly independent rows and columns, you can use these rows and columns themselves as the basis that spans the row and column space. So when the matrix HR is exactly rank R, what you need to do is you need to find R linearly independent rows and columns. If you do this, then you can form a factorization that essentially takes the column matrix times a matrix in the middle, which has different names. U matrix could be skeleton matrix, and then multiplies by the rows here. So I and J are just the indices of which rows and columns you choose, and the benefit is that you can compute this factorization in a computational complexity that scales like the rank cube. So if you just assume that the rank is small, you can find this decomposition. Now the issue is that most matrices are not exactly rank R, and so it's not sufficient to just choose rank R columns. What you need to do is you need to find good column rows and columns that you want to choose. And there's a tremendous amount of literature that looks at this. Many doing leverage scores. Many are focused on this maximum volume idea that comes up in all sorts of places. But the general idea that we're going to follow is we want to choose I and J, so again the rows and columns of the matrix, to maximize the determinant of the matrix formed by their intersection. And if we do that, then we can guarantee that the maximum error that we achieve is bounded by the singular value that we left out and the term that scales with R. So the idea is then if the matrices that we're considering have a decaying spectrum, we can use this to guide the rank that we choose. Now, in general, this is a combinatorial optimization problem, and it's infeasible. And so what we do is we use a cross-approximation scheme to solve this problem. And now, briefly speaking, I can provide more details if you'd like. The cross-approximation scheme that we use only requires sampling order dr squared columns, and or only order r squared columns. And the idea is that you sequentially choose a set of columns, then you find rows to maximize the volume of the intersection matrix. Then you fix those rows, and you find the resulting columns, and you keep alternating between switching rows and columns. Eventually, you bring up the volume enough to be stable and enough to be in a regime where this might hold. And so if you have this low-rank decomposition, you can now use the standard eigenvalue realization algorithm to obtain your reduced order model. And the algorithm is simple. It has these 6 steps. So first we're given the Hankel matrix. Again, this is directly computed from the data, from the input-output data that is obtained. And we use cross-approximation to find this reduced order model. Now, to find this low-rank representation, sorry. Now the idea is that we need this orthogonality conditions that we showed on theta and gamma before in order to have this balancing. And so what we need to do is we need a couple of steps. First, we need to orthogonalize the columns and orthogonalize the rows. And then you compute the singular value decomposition of the cross matrix, which is a small matrix. It's R by R, so it's efficient to compute. Then you can form the matrix formed by the triangular components and the singular value decomposition of the cross matrix, and that's step 4. And now you can take the singular value decomposition of this small matrix, which is again R by R, which allows you to form an orthogonal basis for theta and an orthogonal basis for gamma. So the main idea here is that, again, instead of discovering reduced order structure by the singular value decomposition, which needs to, in general, go through every data point, we assume it exists. And we assume it exists by exploiting, and we exploit it by using cross-approximation to the COR. So here's an example where the Hankel matrix is size 15,000 by 15,000. It's a mass spring damper system. And these are the kind of gains that we can achieve. Now here we assume a matrix of rank we don't assume it. We can discover also their adaptive schemes to the CUR to discover the rank. And in general, we find that it discovers a rank around 80. And then we can compare the SVD and the CUR-based eigenvalue realization algorithms. And what we see here is that we have essentially the same order of magnitude error from both of these matrices, but we have 2 orders of magnitude reduction in the computational time. So this is again moving towards this idea that if we can reduce the computational time more and more, perhaps we can start putting these things online. Now, the other thing that I mentioned is that we can prove stability, and I didn't show this, I didn't show the technical result, but in general what that means is that we can also look similar to the previous talk at the eigenvalues resulting from this approximation. We can show that they lie in this circle. And here we actually compare the eigenvalues of the CUR approach to the SVD approach. And you see there are different groupings here. Some are quite accurate, some are actually displaced a little bit. And then we can actually look at the error of the eigenvalues as we approach the limit of stability. So the idea is the closer you go to the limit of stability, you want to make sure that you nail those more accurately, because a slight error will cause an unstable arrangement. And what's nice is that we see that this indeed is something that we observe. As we get closer to this boundary, and in general, we have quite accurate reconstruction. And if we then look at the simulation of the reduced order model from both the SVD-based and CUR-based approaches and compared to the full order model, we see that it's virtually identical reconstruction. And so we have we show this effective. It shows the approach is effective. Okay, so now I'm going to switch gears a little bit. So here, this was learning a very in a regime linear time invariant systems where we can prove things. Things are nice, and we can essentially make a existing algorithm more computationally efficient by replacing it with a different low rank decomposition. Now we'll look at the example of a different context where we have a dynamical system and we want to learn this F. This F might be high dimensional and it's going to be in general non-linear. And so again, I want to remind the criteria for the representation that we want to choose. We want an F is going to be real valued in general because this is going to be describing most of the dynamical systems of interest. We want it to be expressive. So we want it to be able to have very complex representations, but not require a lot of data. So essentially a few parameters, but still expressive. We want it to be simple and interpretable, and the main reason why we want it to be simple and interpretable is because we're going to be using it for control. We want to be able to potentially learn representations that are amenable to analysis. And finally, we want something fast to compute with. Again, that's going back to the idea of building algorithms whose components are models learned using data-driven methods. So I'm going to start with the general shallow learning setting. So F is going to be represented in a set of basis functions P. So this, we've already noticed that we've already seen this all over the place, for instance, in SIMD or in linear regression. And it's really everywhere. And usually what this means, this hides the fact when this is written like this, that in multidimensional settings, these psi's are actually tensor products of univariate polynomials. And the reason is we don't know how to deal with multivariate functions very well. So we can only build multivariate functions using univariate functions, and tensor products happen to be the way that we know how to do this. Now, in general, this could be anything. Now, the problem is that this is the curse of dimensionality, and this is one of the reasons why kind of shallow learning doesn't work very well. It's in the sense that if you want to, as you increase the dimensionality, maintain expressivity, you need an exponential growth in parameters, but then you need exponential growth in data, and you can't afford this. So one thing that this is an expressivity issue I'll get back to in a second. The second thing is that we want to embed this framework for this representation into a learning scheme. And again, there's many ways of doing that. For example, ridge regression shown here, sparsity-inducing regression like L1 or L0, or the other methods that were really nicely presented earlier today. But again, in high-dimensional settings for large scale, for large number of input settings, even constructing psi and storing theta could encounter the curse of dimensionality. If you limit from tensor product basis functions to, for instance, total order expansion, you still get exponential growth in terms. And then if you only focus on lower order expressions, that's going to limit your expressivity. So the idea is, again, we're going to maintain this structure where under the hood we have an exponential growth in number of unknowns, but we're going to assume that it has reduced order structure. And we're going to then exploit this reduced order structure, but now this reduced order structure is in the form of a tensor. A tensor decomposition, the number of dimensions of the tensor is the number of inputs to the function. So what I mean by low-rank structure, maybe the simplest representation could be an extension of the matrix SVD. So if you think of the matrix SVD as representing a matrix by the outer product of vectors, you can think of a simple tensor decomposition, for instance, the canonical polyadic decomposition, as an outer product of vectors as well. Now there's just 3 of them for a 3-dimensional array. Now, this canonical polyadic decomposition is one out of a zoo of types of tensor decompositions. Each one represents a different type of low-rank structure. However, they all tie back to different notions of separation of variables. And I'll get back to that and show how it enhances interpretability. One nice representation that is a little bit nicer than the CP in the sense it's also more expressive but still limited number of unknowns is this functional tensor train decomposition. So it was first written down like this by Selvitz in 2013. We came up with some algorithms for computing it in 2019. But the idea here is that we have a multivariate function. We're going to represent it as a sum of products of some univariate functions, but in a little bit more of a complex format where it's just maybe more easily to visualize as a product of matrix value functions. So if we want to evaluate the function at a d-dimensional function, we have to multiply d matrix value functions. And each of these matrix value functions consists of a set of univariate functions. Okay, so now we've converted the problem from one of representing a multivariate function to representing dr squared, essentially univariate functions. But univariate functions are simpler to represent and parameterize, and so this buys us some expressivity at the sake of minimizing the number of parameters. Now, as I said, there's a large number of ways to parameterize univariate functions, and you can use whatever your favorite parameterization technique is. For instance, you can do it in a linear basis of, for instance, polynomials or half functions or whatever, or in a nonlinear parameterization where you, for example, represent it in real basis functions where you try and tune where you want to place the centers. In each case, you can come up with gradient-based optimization procedures similar to backpropagation and use all the standard machinery of machine learning to do a gradient-based training. Now, as an example of what this looks like, to tie back to the CUR, in two dimensions, or for a bivariate function, the tensor train decomposition is the CUR decomposition. And the way to see this is that you can take a function of 2 variables, and you can split it up as a vector value function of x times the matrix. So this is the skeleton matrix times the vector value function of y. And now the challenge is to represent this each of these univariate functions of x and then y in some basis. For instance, in a basis of polynomials or half functions or whatever you want. And then you have to store the parameters of each row and column, and this has PR plus R squared parameter. Another example is an additive function. So in high dimensions, you might have a function that you want to parameterize in this additive format. And in the functional tensor train representation, it also has a simple form that has this lower triangular structure, where you can try to see that if you multiply this vector times this matrix, you have f1x1 plus f2x2 and then a 1. So then as you keep going along and along, you accumulate these sums of these univariate functions. So many representations that you can think of and can have a nice representation in a low rank format, in particular in the functional tensor train format as well. And so one thing we can do is we can take this format, we assume that the representation satisfies this low rank format, and we put it into the optimization routine and then do standard backpropagation. So the idea is, again, we have this least squares objective, but now our constraint is going to be the space of functions that are low rank, and in particular of rank less than or equal to R. And the gradient computation in this case, we can do very efficiently also in the computational complexity that scales like dr squared. So if the number of parameters in each of the univariate functions that are underlying this representation is p, you have a nice computational complexity that instead of scaling exponential with dimension, scales linearly with dimension, but now quadratically in this new parameter that measures complexity called ring. So the point of this slide is to show that not only is this low rank decomposition useful in some targeted settings, which we knew on speed and representative quality, we actually applied it and compared it against 22 other algorithms on time data set, and it's competitive for general purpose representation algorithms. So here we compared it to, for instance, parametric approaches like lasso-based sparsity with, for instance, random trees approaches, boosted regression, all sorts of different algorithms. And for this kind of test case where we use the same tuned parameter settings for each case, we don't do it case specific, it turns out that it's quite accurate, second best overall on all these things. So going back to the system ID case, we have this general purpose mechanism by which to learn models from solving least squares problems. So anywhere where you can pose a least squares problem, you add this low rank constraint, and you can use these methodologies. So for instance, if you are familiar with SIND, which was introduced earlier and widely used, you can frame a least squares problem in the same way, but instead of having a sparse regularization, we're not going to have a low rank constraint. So if we do this, the goal is to for example, to train up to a certain amount of data and predict in the future. And one nice thing with the low rank approach that we can do is we can actually learn a low rank representation simultaneously of this multi-output system. So individually, if you look at this function is rank 2. So you can analytically write it out by hand, but you can also see that together, this function is low rank as well. And you can leverage this to reduce the amount of data needed in order to accurately reconstruct the model. So here we see that if we learn all the outputs simultaneously from data up to 2 seconds, we can accurately predict up to 20 seconds. Whereas if we independently learn from each output separately, we struggle to have kind of long time predictions. Now I'm going to come back to this concept of interpretability, and interpretability in the context of low rank decompositions come back to separation of variables. So the idea is that we're going to represent multivariate functions as sums of products of univariate functions, and we can visualize these univariate functions in this way. So here we have these matrix value functions for the first output of the learn 63, and you can see that it learns that these functions should be linear and quadratic terms. I did not constrain it to only include these. These were obtained from data. And so now you can go around and you can use this type of structure for very efficient computations. For instance, if you need to marginalize along certain variables or do other types of techniques, or if you want to interpret where complexity comes in, for instance. So we see that the second order model has quadratic terms, but the first one doesn't. You can do this type of analysis maybe from models that you don't know, for instance, what else. So I don't want to stand in the way of lunch, so my takeaway is that if you assume structure exists and then try to exploit it, instead of discovering that it exists, you can achieve tremendous computational gains. You can have code on my website, on my GitHub, and here's several papers that I discussed. So thanks.
Megan.
So you mentioned that you would assume that there's structure that exists, and forgive me if I'm assuming that when you say high dimensional, it's not as high dimensional as maybe I'm assuming, but assuming it's very high dimensional. Have you compared how this holds up to, for example, randomized linear algebra and using that exploitation of eigenvalues of the orthonormality that the matrix can provide of randomized linear?
Yeah, for instance, with the Cor decomposition,
yeah.
you could do randomized linear algebra approaches. Now, typically, and correct me if I'm wrong, many linearized randomized approaches require still applying the matrix to the vector, and would be an n-squared operation. Now, if you want to do it, maybe only one scalar vector, maybe it could be lower. But this can potentially be below n-squared because it only needs r columns and rows.
Other questions?
They are ready for lunch. Hey, everybody, listen, we got about an hour and a half, 45 minutes for lunch. Be sure to be back a little bit before 2, because Michael Brenner will be having this, the second of the keynotes. Like I said, a lot of great options. And if you're asking, yes, the Chipotle is right up there. Just 3 blocks. But otherwise, tons of stuff. We'll see you back here. Thanks again, Alex.